Welcome back. This is section 6.5. We are applying systems of linear equations. We are going to apply all the different methods that we've learned to solving systems of equations. We're going to try to apply the best method for the particular problem. There's some strategy with that. You can use graphing, substitution, and elimination for any system, but sometimes it's a little bit more difficult if you try to substitute when you should really be using elimination, or if you're trying to graph when you could actually substitute. So we're just going to fill in this table of all the different methods and when it's best to use each method. So best time to use graphing? Well, first of all, if the equations are in slope-intercept form, y equals mx plus b, you don't have to do all of that work trying to move things around, subtracting things, dividing things to get it in that form. Another case is if you're asked to, you're going to have to do it. Okay, it gives a good visual. So if you're looking for a picture, and maybe you're not just concerned about when the two items are equal, but maybe you're looking at a bigger picture. Maybe you're comparing cell phone plans, and the slope of the lines determine which plan is better for what type of data usage or not. So where it would intersect would tell you where the two plans were equal, but the graph would give you a little bit more information than just when they're equal. And then maybe if you only need to estimate. Graphing, sometimes it's really hard to pinpoint exact solutions if they're not whole numbers. Substitution is best if one of the variables has a coefficient of 1. So maybe something set up along the lines of this. X minus 3y equals 5. It's really easy to isolate that x value by just adding 3y over to the other side. A simple addition or subtraction to get the variable by itself, and then you could substitute. Another reason you'd want to use substitution or the time is when one of the equations is solved already. So if you already had x equals something or y equals something, it's easy to just plug in. It's when there's more involved, where you'd have to add or subtract and division is involved, that elimination kind of comes into hand. So if one variable has a common coefficient, if you see a 3x with another 3x, or a 3x with a negative 3x, you know that if you add them or add the opposites, they'll eliminate. So that might be a better case than trying to solve and get one of the variables by itself using substitution. Elimination with multiplication is best if, you know what, everything's just a mess. You got non-matching coefficients, it's in standard form, it would be a pain to put it into slope-intercept form. It'd be very difficult to solve for one of the variables for substitution. So you just make the equations, you manipulate them to make them do what you want them to do. So let's go ahead and we're going to also apply not only these methods, but we're going to take it to another level of word problems. So now that you've been practicing systems, it makes problem solving with words a little bit easier. You're going to choose two variables. Make the variables make sense to the problem. If you're talking about perimeter, length, and width, use L and W. If you're talking about people, use the initial of their names. So a lot of times if you make the variables match, it helps your brain process the math. Write two equations, read carefully, and look for key words. If you're going to solve for two unknowns, you have to have two equations. You can solve using any method. So once you have your equations, it's best to go back through that chart and figure out which scenario, which method works best for that scenario. And you're going to write your answers as an ordered pair. So let's go ahead and go through this one. This one doesn't have a story, but let's talk about the best method. So I look at that, and I'm going to go through my methods. Graphing would be awful. We'd have to solve for y. They're not in slope-intercept form. I am not graphing. Substitution isn't that bad. If you notice, this x right here in the second equation is all by itself, or it has a coefficient of 1. So to make it isolated, to get it by itself, we just simply have to subtract a 2y from both sides. Elimination, I'd have to use multiplication. So I could multiply by a -4 if I wanted to. I'm going to stick with substitution here. I think it's pretty easy to just move over the 2y. So I'm going to subtract 2y from both sides. And that gives me x is equal to 14 minus 2y. If you would rather put the negative 2y out in front of 14, that would work too. Since I am using the second equation, I have to plug it into the first equation. So I'm going to replace or substitute the x value in the first equation with 14 minus 2y. So I end up with 4 times the quantity, 14 minus 2y, minus 3y equal to 12. So notice there's no more x involved in the equation at all. And so we end up with 4 times 14, which is 56, minus 8y minus 3y equal to 12. And then I have negative 8y's and negative 3y's. That means I have negative 11y's. So I just combine them together, is equal to 12. So I got 56 minus 11y is equal to 12. I'm going to subtract 56 from both sides. Negative 11y is equal to negative 44. I'm going to divide both sides by negative 11, and y is equal to 4. Not done yet. I have to find my x value, so I'm going to plug that 4, substitute that 4 into the other equation. It's all set up to solve for x. X is equal to 14 minus 2 times 4. X is equal to 14 minus 8. X is equal to 6. And so my solution is the ordered pair 6, 4. Okay? So you wouldn't be wrong if you chose elimination. It's just maybe it would take you a little bit more time. Or, doing it with substitution and then checking it with elimination is an excellent strategy, especially on test or quizzes. All right, for this one, a couple different methods here. We could substitute. Substitution would be pretty easy here. We could also just do a quick little elimination if we wanted to. I would use substitution as well in this case. So I would just replace, if y is equal to x, I would replace this y with x. 4x minus 2x equals 14. That gives me 2x is equal to 14. Divide by 2, x is equal to 7. If x is equal to 7, I plug it into the other equation, and that means y is equal to 7. Pretty simple problem. So my answer is the ordered pair 7, 7. Sometimes the easy ones, we overthink them. All right, so let's go ahead and try some word problems. The first of the word problems. Zach has volunteered 50 hours and plans to volunteer 3 hours in each coming week. Allie is a new volunteer who plans to volunteer 5 hours each week. Write and solve a system of equations to find out how long it will be until they have volunteered the same number of hours. The same number of hours means that they'll be equal. So when will Zach equal Allie is the question here. When they talk about how long, they are volunteering on a weekly basis. So I'm going to let W equal my weeks. And I'm going to write an equation for Zach, and I'm going to write an equation for Allie, and we're going to set them equal to each other. This actually has just one variable. You could use just one variable. We're talking about volunteering, and we're talking about time. So Zach's time volunteering, he's already volunteered 50 hours, and then he plans to add on to that 3 hours per week after that. Allie has not volunteered at all. She's new, so she's going to volunteer 5 hours per week from here on out. So she's volunteering more hours per week, but Zach has more hours to begin with. So we want to know, when will these two balance is the question. 50 plus 3W is equal to 5W, and so we would subtract 3W from both sides. 50 is equal to 2W divided by 2. W is equal to 25. So they asked when would they be equal, when would they be balanced, and that the answer is after 25 weeks. So that one we really can't use an ordered pair for because it really wasn't a system at all. Just a nice word problem that's setting things equal to each other. Let's look at the next one. I'm not going to read it to you. Go ahead and read the problem. If you need to pause, go ahead. So I think it would be best in this case to define a variable. H is the number of hot dogs. And P is equal to the number of pops. There's two different scenarios here. There's two different situations. One of the situations, $5.25 to buy 3 hot dogs and 2 pops. So 3 times H plus 2 times P is equal to $5.25. The second scenario, we bought more pops, less hot dogs, and it cost us $6.25. So just make sure you line things up. We've got 2 hot dogs plus 5 pops is equal to $6.25. Looking at this problem, I don't want to graph it. Looking at this problem, I really don't want to use substitution because isolating a variable would be difficult. So I'm going to solve using elimination with multiplication. So I need to multiply. I first got to choose which one I want to eliminate. So I'm going to pick H. To make H go away, I need them both to equal 6. That's the smallest number that 2 and 3 both go into. So I'm going to multiply the top by 2, and I'm going to multiply the bottom equation by -3. Don't forget to do both sides. I'm actually going to put the 2 and the -3 on the other side as well. So I'm multiplying both sides by that. When I do that, I end up with 6H plus 4P is equal to 1050. And on the bottom, I end up with a -6H minus 15P is equal to -1875. When I add these two columns together, I end up the H's cancel. -11P is equal to -8.25. It's okay. I know we're talking about money and pops and hot dogs. They can't be negative, but they will cancel. I would divide by -11, both sides, and the negatives will cancel. P is equal to 0.75. And so the cost of a pop is 75 cents. We need to plug that back in so that we can find the cost of the hot dogs. So I can just use the original problem. I'm going to use the first original problem to find out how many hot dogs. So I'm going to say 3H plus 2 times 75 cents is equal to $5.25. That means 3 hot dogs plus the 2 pops at 75 cents each is $1.50 is equal to $5.25. We're going to subtract $1.50 from each side. That gives me 3H is equal to $3.75. When I divide both sides by 3, that tells me that the number of hot dogs is $1.25. So each hot dog was $1.25. If you want to write that as an ordered pair, that's fine. Your solution then, H comes before P, $1.25 and 75 cents. In a word problem, I really don't care to worry about the actual ordered pair part. It's telling a story. So I would say hot dogs cost $1.25 and pops cost 75 cents. Okay, the next one, we're going to set it up, but I'm not going to actually solve it with you, okay? We'll talk about the strategy, but for time purposes, we'll wait. So the sum of two numbers is 70, and then they describe the two numbers. So I'm going to make x equals my first number, and I'm going to make y equal my second number. And so the sum of the two numbers is 70. x plus y is equal to 70. One number, let's just call that x, is equals 10 more than twice the other. So x equals 10 plus 2y. Based on the information I'm given, I would use substitution. I would take this x value that's already set up for one variable and plug it in here. And you would use substitution to find the two numbers. If you would like, go ahead and solve that one. You would end up with the answer 50 and 20. X is 50 and y is 20. I'd be happy to check your answers if you do not get that. And the last problem, it deals with an age problem. Serena and Jordan. So since we're using Serena and Jordan, I'm going to define S is equal to Serena's age, and J is equal to Jordan's age. I need to create two equations using S and J. Serena is older. That's important when we talk about subtraction. The difference in their ages, we're going to subtract their ages, is equal to 12. So to subtract and get a positive 12, that tells us that we're subtracting Jordan from Serena, and it equals 12. If you do that in the opposite order, it will not work out. The sum of their ages, S plus J, is equal to 50. This one's all set up to use strictly just elimination. I've got common coefficients. My J's are opposite signs. No need to adjust. You simply add the two equations. 2s, the J's cancel, is equal to 62. Divide by 2, both sides. S is equal to 31, which means Serena is 31. Plug it in to either one. If I plug it into the first one, 31 minus J is equal to 12. Subtract 31 from both sides. You get a negative J is equal to a negative 19. So that means that a regular J is equal to a positive 19. So that means Jordan is 19. So Serena is 31 and Jordan is 19. All right, so your practice problem, it involves a problem from the book. And I am going to paste that in here right now. Okay, so here's the problem. You can figure it out in the box. There's parts A, B, and C. You're going to write the system, figure out what method you want to use to solve it, and then solve the system. Good luck.